Right, so here we can see some deviations from the ionization energy trend. When we compare beryllium to boron, beryllium has a higher ionization energy compared to boron. When we look at the electron configuration for beryllium, the electron that's being removed is from an S subshell. For boron, the electron being removed is from a P subshell. So the energy of the subshell increases as L increases. This means that an S electron is harder to remove from an atom than the P electron in the same shell. Deviations for oxygen versus nitrogen. So oxygen has a lower ionization energy compared to nitrogen. So removing one electron from oxygen will eliminate the electron repulsion caused by pairing electrons in the 2p orbital. It's easier to remove that electron than it is to remove an electron that's in an orbital by itself. Removing an electron from a cation is more difficult than removing an electron from a neutral atom because of the greater electrostatic attraction to the cation. Likewise, removing an electron from a cation with a higher positive charge is more difficult than removing an electron from an ion with a lower charge. Thus, successive ionization energies for an element always increases. So that means that it takes higher energies to remove electrons from atoms that are positively charged. So the higher the positive charge, the greater their energy. So we see that here. If we have potassium, if we remove an electron from neutral potassium, it takes an ionization energy of 418.8. Okay, and then if we remove the second electron, its ionization energy jumps up to over 3,000. Then you see the trend from left to right here. The values are increasing, and so that's just the general trend for ionization energies. The increase as you go from as you increase the number of electrons being removed. At some point, there is always a large increase in successive ionization energy for an element. This large increase corresponds to the removal of core electrons, which are harder to remove than valence electrons. An example, scandium and gallium both have 3 valence electrons. The large increase in ionization energy occurs after the third ionization energy. And that's true for sodium. The second ionization energy will be removing a core electron. For magnesium, the third ionization energy will be removing a core electron, and so on. The last topic we're going to talk about in this section, in this chapter, is referred to as electron affinity. So the electron affinity is energy change for the process of adding an electron to a gaseous atom to form an anion. So here's an example of a neutral element. We're adding an electron in this case, okay, to produce an anion. Okay, so that's an activation or electron affinity value of 1. So that means one electron was added and it has a certain electron affinity value associated with it. The process can be exothermic or endothermic depending on the element. For some elements, energy is released when the gaseous atom accepts an electron. Okay, in that case, it has a negative electron affinity. For other elements, energy is required for the gaseous atom to accept the electron, and that is associated with the positive electron affinity. It becomes easier to add an electron as the effective nuclear charge of the atoms increases. Electron affinities become more negative across a period. There are some deviations from this trend. Okay. So let's look at our trend first, and we'll come back to wrap this up here. So here we have electron affinity. So electron affinity increases as we go across a period. Okay, and it makes sense if you think about nonmetals. They already have a lot of valence electrons. They want to add another electron if they can, so electron affinity is going to be high. Metals want to lose electrons, so they would have lower electron affinities. Alright, what about the trend up and down? So electron affinity increases from the bottom up. The smaller the atom is, the greater the pull for electrons, and it wants electrons. If you think about smaller atoms, they have a greater pull for electrons anyways because they don't have many electrons that are repelling each other. So electron affinity is going to increase with smaller sized atoms compared to larger ones. There's some deviations in electron affinity trend. The noble gases in group 18 have a completely filled shell, and the incoming electron must be added to a higher energy level. And so, of course, they don't want electrons, so of course they would have a very low electron affinity. Group 2 has filled S subshells, and so the next electron goes to a higher energy P subshell. Group 15 has half-filled P subshells, and the next electron must be paired with an existing P electron, and so that creates deviations there. In all of the cases, the initial relative stability of electron configurations disrupts the trend in electron affinity. Okay, so you can see that demonstrated here. Here's some of the electron affinities for selected elements, and you can see how the values for each element here, and notice how with the noble gases you have very little electron affinity, and for fluorine you have a very large electron affinity. For metals you're going to have small values here. And again, they're, depending on where you are, of course there are some deviations from the trend. All you need to do though is to memorize the trend and you should be in good shape. Alright, so let's do a couple problems from the chapter. This is example 6.12 from your textbook. They're wanting us to predict the covalent radius, the trend for this, okay? And so which one is the smallest, and then so on. Okay, so we're going to predict from least to greatest the size for each element. And so in order to do that, we have to really look at the periodic table. So I'm going to bring that here. Okay, so we're going to look at germanium here, and then FL, which is, where's FL? Alright, so I'm going to pick a periodic table that's okay. Let me go to an actual whole periodic table right here. Okay, FL is right there. Alright, pick a periodic table without the element. Wonderful. Alright, so FL is right here. It's one of those new elements that I don't even have on my periodic table in my classroom, so that explains why I'm scratching my head here. Alright, so FL, fluorium there. Alright, Br, bromine, and then Kr, krypton. Alright, so let's figure out which one's the smallest of these four. Okay, so germanium's here, bromine and krypton. So they are all in the same period here. And we have germanium and we have fluorium here. So we're going to see the smallest one. So we know the trend from left to right for atomic radius. As you go from left to right, elements get smaller, right? So the smallest element then would be krypton. Okay, and then the next would be bromine, and then the next would be germanium, right? And then comparing germanium to fluorine. Fluorine's lower. Remember the trend from top to bottom, the atoms get larger. So the largest element here would be fluorine. Right? So basically your ranking here would be krypton is less than bromine. Right? Krypton's less than bromine, which is less than germanium. Okay, germanium's larger. And then the largest would be fluorine. It's furthest to the bottom, and it's the furthest. It's actually left of bromine and krypton, but it's below germanium, so it's larger than germanium. Okay. All right. Next example here. Example 6.13 from your textbook. So this one's a little see, it's slightly complicated. Okay. So it has, it doesn't just list different elements. It specifies the ionization value, okay, for each element, okay. So here is the first ionization energy for aluminum, the first ionization energy for TL, which is thallium, the second ionization energy for sodium, and the third ionization energy for aluminum. Alright, so one thing that jumps out to me is I know sodium forms +1 ions. So it's removing its second electron. So I know that one's going to be really, really high. The value is going to be high there. Okay. Also, I know because its second electron is being removed, anytime you have a second electron removed, it's going to have a higher ionization than a first energy electron removed. So, next I see the same elements here. One has 1 electron being removed, one has 3. I know this one's going to be larger. The third ionization energy is going to be larger than the first. Okay, so I know that one's greater than that one. I know this one's going to be less than this one because it's just first ionization energy. Okay, so the question is, which one is it going to be? Have lower energy for thallium or for aluminum? And if you think about the size, thallium here is towards the bottom, aluminum's up. So it's easier to remove an electron from a larger atom than it is from a smaller. So that means I know that 1ie1 for thallium is going to be smaller than all of them. Okay. Okay, so I eliminate that one. The next, so I know this one has to be next, right? Because it's a 1e as well. So 1e, 1 for aluminum is going to be less than the third electron for aluminum. Okay. And then I'm left with 1e for sodium, the second electron removed from sodium. Okay. And again, that's one of those exception things. I'm sorry, I'm writing the answers and I'm not showing them. But so my trend here would be first electron from thallium is less than that of first electron from aluminum, which is less than third electron from aluminum, which is less than second electron from sodium. How do I know this isn't larger than this? Well, I know that sodium forms +1 ions, okay? I know aluminum forms +3. So honestly, I think, this energy is going to be less than it would be for this one because sodium is going to have a noble gas configuration before that second electron is being removed. Okay. Aluminum's not. Aluminum's actually going to have a noble gas configuration after the third electron is removed, whereas sodium is going to have a noble gas electron configuration before it's removed. So it takes more energy to remove that second electron from sodium. Okay. So these are the things you have to think about when you're trying to rank different elements based off of ionization energy or atomic radius. Okay. Alright, so last thing I want to show you, and then we'll wrap up the chapter, and that is the periodic trends. And just to remind you to sketch the periodic trends on your periodic table. Okay, remember that the arrows are pointing in an increasing direction, so going from bottom up is increasing electron affinity. From left to right, you're increasing electron affinity. Atomic radius increases from the bottom down, and from right to left, atomic radius increases. Ionization energy increases from left to right and from the bottom up. Okay, if you notice electronegativity and electron affinity, those trends run the same way. The definition is a little bit different for electronegativity than it is for electron affinity, but the concept is the same.